All right. So just in the previous class, okay, just in the previous class, I asked you two things. Can you see A and B? Can you see the one parameter bifurcation diagrams in A and B, and let me know whether the same dynamical behavior or different dynamical behaviors. And some of you, there are a lot of people who said that A and B represent the same dynamical behavior, that is chaotic dynamical behavior. Saw that A and B are representing different dynamical behaviors. Okay, we saw A and B actually represent different dynamical behaviors. Why that is the case? The eyes which you are seeing, the one parameter bifurcation diagram, can be deceiving sometimes. So therefore, we need a characterization for this. That is Lyapunov exponents. Okay. So as you can see on the graph below, which is corresponding Lyapunov exponent for the A is very close to 0. So if the Lyapunov exponent is very close to 0, it is representing a quasi-periodic orbit. Okay, and you can see that it is 0 almost in an interval, in this interval itself. Okay, some points where it is just touching 0 and coming back. So those kind of points represents the bifurcation point. And I told you that you can match up these lines like this and see that this is a point touches 0 and coming back. So therefore, this kind of points which you see are the bifurcation points, and they doesn't imply quasi-periodicity. There the Lyapunov exponent is 0 and you might feel that it is quasi-periodic, but actually it is just hitting there and coming back. So therefore, it is representing a bifurcation point. But this scenario you can see, it is totally 0 throughout the interval. So therefore, it is quasi-periodic. Okay. And what about region B? In that region B, you can see that Lyapunov is positive here. So therefore, this part is quasi-periodic. Region A is quasi-periodic, and region B is chaos. Okay. So it can be asked in exam, written A, B, C, D, and throughout, and you have to analyze this whole figure. Okay. So try to, this is a fundamental concept, try to read about it. So therefore, we came across something known as a Lyapunov exponent. So, yeah. This is something known as Lyapunov exponents. What is Lyapunov exponent? Lyapunov exponent, like, I'll just tell you that it is a number. We denote it by lambda. Yeah. So if it is a 1D map, you will have one Lyapunov exponent. If it is a 2D map, you will have two Lyapunov exponents, lambda 1, lambda 2. If it is a 3D map, you will have three Lyapunov exponents, lambda 1, lambda 2, lambda 3. Additional chaotic map, you will have n Lyapunov exponents, that is lambda 1, lambda 2, lambda 3, so on till lambda. It's clear, right? Clear? Similarly, it is not just restricted to maps, it can be flows also. So 1D flows, 1D flow also has one Lyapunov exponent. 2D flow also has two Lyapunov exponents. Similarly, ND flow will have n Lyapunov exponents. Fine. Now, we will just fix our study for the maps. It can be extended to flows also. Okay. So if in any case, if at least in your set of lambda i's, the set of Lyapunov exponent, if at least one of lambda I is greater than 0, that implies chaos. If at least one lambda I is positive, it implies chaos. Okay, got the idea? Suppose your Lyapunov exponent is 3.2 minus 2.8. What this is? Is it chaos? Yes, because positive, at least one of them. So this is chaos. Suppose 3.2, 3.6, minus 3.6. Is this chaos? Yes, it is chaos, but it is even more than chaos because there are two Lyapunov exponent positive. Okay, two Lyapunov exponents positive. So this is known as something more than chaos, and it is known as hyper chaos. Okay, fine. Okay. Hmm? Now this is about chaos. Suppose I'll tell you. So if all lambda i's are less than 0, then this is, if all lambda i's are less than 0, all lambda i's, all Lyapunov exponents are less than 0, then either it is a fixed point, that is steady state, or can be periodic orbits. Okay. 3. If some lambda I is close to 0, then this is quasi-periodic, which you just saw before, isn't it? So these are the characterization you usually use to see for chaos, quasi-periodic orbits, periodic orbits. Okay. Now we will see why that is the case, that if lambda is positive, then it is chaos. Why it is the case? So do you know what is chaos? What is chaos? What is chaos? Chaos is a property which shows sensitive dependence to initial conditions, isn't it? Yes, how many of you agree to this? Sensitive dependence to initial conditions. Yes, you knew that, no? You did this experiment also for Hanon map. What you did with Hanon map? You plotted the time series of a chaotic attractor. In that, what you did? You started from this initial condition and you iterated the map. So just, we should not draw the lines, but just for visualization. Okay, just for visualization. Then what you did, you started from a nearby point. You started from a nearby point. Can you see that just a tiny change in initial condition is leading to huge difference in output? Isn't it? Otherwise, what would have happened? It would have just shifted by something and would have followed the same pattern. But it is totally different. So therefore, it is sensitively depending on the initial condition. A tiny change in initial condition can lead to a huge difference in the outcome of the final behavior. That is known as chaotic dynamics or chaos. Okay. Now I will tell that. But just think about initial condition now. Small change in initial condition is leading to huge difference in outcome. Just remember that. We will use that concept in Lyapunov exponent and see that Lyapunov exponent will turn out to be greater than 0 for that to happen. So therefore, positive Lyapunov exponent implies chaos. Okay. All right. So yeah. So we'll take two considerations. One is one-dimensional maps. One-dimensional maps. In one-dimensional maps, we will find the Lyapunov exponents. Then we'll go to higher dimensional maps, that is 2D or 3D maps. There we will see that it's not that simple. It depends on something more. Okay. So those are the highlighted concepts I will tell. We will not go too much deep, but I will show that in some cases you can actually find the Lyapunov exponent analytically. That will be some important questions. Okay. You can expect a heavy question from this class today. Heavy question, around 20 marks. You can expect from this class. Okay. It's very important today. So try to learn this as much possible, all the concepts, because it will be a long question and graphical also. A, B, C, D can be asked, and yeah. Okay. So Lyapunov exponent is just Lyapunov exponents. It's a simple way to characterize the dynamics. A simple way to characterize the dynamics of a chaotic system. So we begin with 1D map. Just start with the simplest case, that is 1D map, how Lyapunov exponent looks like in 1D map. So it's a 1D map, right? How many Lyapunov exponent will it have? One only. Okay, so we'll just have a number lambda, and that is our Lyapunov exponent. We will not have more than that. Okay. So consider a general 1D map. General 1D map. Can you say how it looks like? Say xp plus 1 equals to f of xp. It is fine. Instead of n, I have just used p. You understand this? This is the recurrence relation for the 1D map, how the dynamics occurs. And moreover, I restrict my x values to only lie in between 0 and 1. Okay, x is lying in only 0 and 1. X only can take values from 0 and 1. Okay, fine. Okay. Suppose, so this is how I'm deriving for you the Lyapunov exponent. I'm deriving, I'm not suddenly giving you the expression for Lyapunov exponent because you will not get any intuition. I have to derive it. I'm deriving it now. So just keep patience and just think. If you're not getting some parts, it's okay. But just have some intuition knowledge about this. Okay. So suppose F has a periodic orbit. Suppose we have a periodic orbit of periodic orbit of period P. So what does it mean? Yes, how can we say that mathematically? Suppose you started from x naught, okay? Then you keep on iterating, then you landed on xp. Then if you iterate that xp, you will be back to x naught again. That is the idea, right? X naught, x1, so on till xp. Got the idea? So what does it mean? What does it mean? xp is equals to fp of x naught. Isn't it? This is clear for most of you, no? Agreed? Okay. So what is the orbit here? Our orbit is x naught, then x1, x2, so on till xp. This is a periodic orbit, right? So you start from x naught, keep on iterating. You reach xp, then again it will go to x naught if you iterate. That's a periodic orbit. It will keep on recurring. Okay. Now we want to understand. Now we want to understand the stability of this orbit. How this orbit is stable. You know how when the orbit will be stable? You know Earth's orbit is stable. Earth's orbit, the orbit Earth is moving, it is stable. Why it is stable? Can you say? Like according to dynamical system perspective, if you vary, if you just disturb Earth position, if you just push it, like disturb the position of the Earth quite a tiny bit, then it doesn't get affected. It will come back to its original position, to its orbit. Okay, but you can see, like if someone pinches you here on a flat surface, you just get displaced, right? But over the edge, you will be standing, and if someone is pinching you, you will fall, because that's the point where it is unstable. A tiny pinch, a disturbance in your position can shift your dynamic. But flat surface. So if you are here, then if I am pinching you, then you can just slide through. You won't fall. Got the idea? That is what stability means. Okay. So here also we will do the same. Here you have the periodic orbit of period P, x naught, x1, x2 up to xp. What we will do here is just take a perturbation to it. Just displace it and see whether it is coming back to itself or not. That is what is stability. If it comes back to the same position, it is stable. If it is not coming back, it is going somewhere else, then it is unstable. Got the idea? Anyone issues? Any having issues? Think about it. So I want to understand the stability of this orbit, stability of this periodic orbit, stability of periodic orbit. So what shall we do? So xp is a periodic point. Agreed? xp is a periodic point. isn't it? X naught is also a periodic point. X naught is also a periodic point. Not getting any vibes. Yes, no, I'm see. Okay, I'll tell you this way. X naught, then you iterate the map, you land to x1, iterate the map x2, iterate the map x3, so on. This is xp. After, if you iterate the xp, then you will rank. That is a periodic orbit, right? Huh? Now my question is very important question, which I just gave two examples. If I disturb, if I disturb the orbit at x naught here, this is x naught plus x naught plus delta naught. It will be just shifted by delta naught, no? Read. I took plus. You can take minuses. Doesn't matter. But then I will take minus of minus delta naught plus. See, just we can do simple things, not complicated things. So x naught plus delta naught. Now my question to you is how xp is getting affected. Will xp get affected? Also get affected, right? Because that is following a trail. So xp also gets affected. So if xp is affected by delta p, say delta some perturbation. Xp plus delta p. So if you perturb delta naught for x naught, then the final point will also get disturbed, right? Let I say it is delta p. Okay. Now can you say what is the relation between them? What is the relation between them? Can you tell me what is xp plus delta p? Xp plus delta p is nothing but you apply the p iterations to f of the disturbed point. That is of x naught plus delta naught. Are you getting? So how you reach to so x naught plus delta naught, you iterate again, you reach to some other point, again you reach to some other point, so on till you reach this point after p iterations. Okay, got the idea? Now this is a bit mathematical, so I'm not sure if many of you get it, but I'll try my best. So this xp plus delta p, so you have understood this. We can use a Taylor expansion for this, a Taylor expansion. Okay, how we can use the Taylor expansion? Can you give me an idea? So this will look like fp at x naught plus dou fp by dou x. So just I'm writing the formula I have in my notes. Okay. So see this. It's okay if you are not getting this formula, but it's just a Taylor series expansion, nothing bigger. So can you see that some parts are getting cancelled now? Which part should get cancelled now? Any ideas? Remember, xp is equals to fp of x naught. Do you see xp here? Do you see f of fp of x naught? They are equal, right? So you can cancel them off. Cancel them off. So what you are getting? Delta p is equals to dou fp by dou x at x equals to x naught into delta naught. So you can see that how much perturbation delta p occurred, it is given in terms of the initial perturbation delta naught. So initial perturbation was delta naught, then how much the final point will get disturbed? That is delta p. And you are seeing how much delta p is perturbation. Is it clear? So we can expand this derivative actually. We can expand this derivative. How can we expand this derivative? Using chain rule? Okay, using chain rule. How can we expand this? Any ideas? Let me know. How can we expand this? No, dou fp by dou x. You have to use that only. Is it correct? Is it correct to write this as dou fp by say dou fp minus 1 and then dou fp minus 1 by dou x? Dou x. Are you getting what I'm trying to write here? Can you tell what should be the next term? Think. See, the idea is you can include all the points of the periodic orbit inside this chain rule. You see, p I included, then p minus 1 I included, then I will include p minus 2, p minus 3, so on till x naught. Nth. There is no nth derivative, no. That's what I'm trying to tell you. See, I took pth iteration, right? Dou fp. So there will be how many derivative partials should be? Yes. So similarly, you have to multiply p times. I'm asking you, let me know the expression next. Huh? Yes, yes. Dou fp minus 2 at xp minus 2, then it should be multiplied by dou fp minus 2 again. Yes. Then divided by dou f, yes, p minus 3, evaluated at xp minus 3. Okay, so on. So on till dou f 2, dou f2 by dou f1 at x1, dou f1 by dou x naught. Isn't it? I think so. This is a chain rule, nothing else. Just the chain rule. Just you have to go and see the chain rule, then you can appreciate it. It's not that intuitive also, but if you practice, you can do. Miss Arya, why are you just laughing out of nothing? I think your mobile is helping for that. Is it? Okay. Okay. So can you help me now? Can you help me now? So what's the next step? What's the next step? What's the next step? I'm missing something here, isn't it? So this whole thing is this one. This whole thing is this, right? It is multiplied by delta naught. Okay. Can I write delta p by delta naught? Can I write delta p by delta naught? Then I will know how much fraction it has perturbed from the initial. Delta p by delta naught means how much fraction it has perturbed from the initial point, isn't it? That should be this whole fraction, dou fp by dou fp minus 1 at xp minus 1 into dou fp minus 1 divided by dou fp minus 2 at xp minus 2, so on, till you get dou f1 by dou x. Agree? What happened? Oh, come. Mr. Akul Murali will come here. Why are you laughing? You saw this big chain reaction. Is it? You are having acidity. Acid reflux. What happened? Anyway, maybe, what? Okay, okay. So rate of change of the function with respect to x, I am denoting by lambda. Okay. So don't worry about this. Lambda is equals to rho f. Lambda equals to dou f by dou x. Suppose lambda is dou f by dou x. Suppose lambda is dou f by dou x. Just the notation you follow. It works like magic. You won't understand why it has taken lambda to be dou f by dou x, but suppose it is taken, okay? Then each of them looks like that. Each of them is having that same term, okay? So you can write that delta p by delta naught is nothing but I can write it as lambda p, okay? Because it is lambda is multiplying everywhere. It's of the same order. It should not. Huh? No. It should be x. Because see, it is x here. Dou fp by dou x. So dou fp is here. This guy cancels this guy cancels this. So on, you will have dx here. Yeah. So therefore, delta p by delta naught is nothing but lambda to the power p. Okay. Mind you that p is positive, isn't it? P is positive. You agree? P is positive. P is a period. So P is positive. Now, I will ask you one question. That based on this relation, can you tell me the future perturbation, that is delta P, should increase? Okay, should increase. That means they are diverging, isn't it? A small change in initial condition delta naught, if it has to lead you vast difference in outcomes delta P, that means delta P should be greater than delta naught. If delta P has to be greater than delta naught, can lambda be negative? Can lambda be negative in that case? Can you have lambda to be negative and since have this to be like diverging initial condition? Yeah, if lambda is negative, then yes, you cannot have this diverging initial conditions. Lambda has to be positive for delta P to grow. Delta P has to grow, right? Yes. So lambda has to be positive because P is positive. So therefore, why lambda has to be greater than 0 for chaos? Because small change in initial condition means delta naught here. Vast change in output means delta P here. For that idea? So for chaos to occur, small change in initial condition should give vast outcome in result. So delta P has to be greater than delta naught. If delta P has to be greater than delta naught, then lambda has to be positive. There is no other option because P is already positive. Okay. Anyway, so yeah, I could have. I'll share you this note actually. Okay. So let me write this expression. Just I have it now here. So remember this quantity h of x. I'll not show you the derivation that, but it is ln of that quantity lambda, ln of lambda, and it is given as this quantity. It is a bit complicated, but don't worry, it will boil it out. Okay. So I think I for each xi. Okay. So this guy is something more important to you. This guy is something more important, and we'll see how this guy is helping us. Okay. This h of x, ln of lambda. So lambda is positive. So do you know ln function, log function, how it looks? How it looks? What is its behavior? Any ideas? No. So basically, h of x is known as the Lyapunov exponent here. H of x is nothing but the Lyapunov exponent here. You can see that the Lyapunov exponent is dependent at which it is calculated. It is not h. It is depending on x. That means at the trajectory, one point, then go to next point, then go to next point, Lyapunov exponent has to be computed at each of the orbits point. At each of the orbit point where the trajectory is moving, you have to compute the Lyapunov exponent at each of the point. So Lyapunov exponent, since it is computed at each of the point of the trajectory, it is a local concept. Okay, it is not a global concept. Like even the trajectory is you are having a period somewhere other chaotic orbit is going on there, then this guy is not bothered about this. If that guy is bothered about this here, then it is a global property. Like you can see country 1 is depending on country 2. It's a global property. Okay, but inside India, if something is happening, that is a local property. Okay, in that sense, I am saying since it is depending on the orbit present here, it is a local property. Lyapunov exponent is a local property. There is something like local and global property which is a bit deep. Don't need to understand, but just I am covering this here. Okay, so this is how Lyapunov exponent is defined. Maybe we can take one example here. So you can see that here that if you rewrite this, you got this, isn't it? Can you take ln on both sides? Like you can see delta p equals to, I can write this as, can I write this as e to the power p ln lambda delta naught? Can I write like this? I can write. It's okay. It's a bit tough, but it's okay. All right. So throughout this, my hope is that you can at least get some sensitive ideas like why chaos is and how to define chaos actually. All right, you can do this. You can do this. Believe me, this is a standard logarithm trick. Okay, you can do this. So from this, what we learned, since p is greater than 0, p is greater than 0 known. This is known to you. Okay, the growth or decay of the deviation. This is very important. The growth or decay of the deviation depends on the sign of ln lambda. Don't you think? Hmm. Yes. Hmm. P is already positive. There is no other. P can't be negative. P is a period. P is a period. So P has to be positive. Okay. So just look into this. This is much more important. Delta P by delta naught is lambda to the power P, right? So rewrite this. Delta P is lambda to the power P delta naught. Then what I did, I used this logarithmic trick to write it in terms of log. So delta P is e to the power P ln. Okay. Yes, agreed. Yeah. Now what I am saying is exponential that quantity. When the exponential can grow, when e to the power x can grow, x is positive. So P ln lambda should be positive. If you want the deviation to grow, P ln lambda should be greater than 0. But you already know P is greater than 0. P is a period. That implies ln lambda should be greater than 0 for the deviation to occur. If you don't want the deviation, ln lambda should be less than 0. Negative. Okay. Now let us calculate. Question. This is an important question. So let us calculate. Take 1D map. For example, this 1D map is given by xp plus 1 is equals to 2xp mod 1. Okay. xp plus 1 is 2xp mod 1. Fine. Can you yeah, x is belonging to 0 and 1 obviously because mod 1 is used. Fine. Now just that you have a taste of these dynamics, how about x naught is say 0.4. Take x naught to be 0.4. What is x1? Can you tell? Yeah, this is exercise for you. Start. We will calculate Lyapunov exponent for this function. If x naught is 0.4, what is x1? X1 is nothing but 2 into x naught mod 1, right? That is 2 into 0.4 mod 1. That is 0.8 mod 1. Since it is less than 1, it is just 0.8. Okay. It forces, no, mod 1 forces x to be inside 0 and 1 only. Otherwise, see, if you don't define mod 1, every time the number gets multiplied by 2, 2, 2, it will go to infinity. We can't study the dynamics. Means mod 1 means you divide by 1 and take the remainder. That's the idea. Modulo 1 is. So therefore 0.8 mod 1. So it's just 0.8 because there is no higher factor than 1. Okay. So what is should be x2? X2 should be 2x1 mod 1, right? So that should be 2 into 0.8 mod 1. So 1.6 mod 1. So just since it is greater than 1, remove the 1 part. That is just 0.6. Okay. 0.6. Got it? What should be x3? 2x2 mod 1. So 2 into 0.6 mod 1. 1.2 mod 1. 0.2. Okay. Got the idea? Divide by 1, take the remainder. Everyone got? Mr. Anandik, you got 1.2 mod 1 is 0.2. Why? Got it? Why not? 1, 1.2. 1 times what is 1.2? Yeah. So this is just 0.2. Modulo is not for periodicity, I would say. Modulo is just keep in mind that modulo is trying to keep your x values inside 0 and 1 only. Okay. Let us not use mod 1. No, let us not use mod. X plus xp plus xp. It's behaving oddly. Xp plus 1 is equals to 2xp. Okay. Can you let me know, like say x0 is 1. What is x1? 2. What is x2? 4. x3? 8. x4? x5? x6? x7? x8? It is diverging. Do you agree that it is diverging? Diverging means there is no interesting phenomena, just so in order to make it the dynamics interesting and to study it, just add mod 1. Just add mod 1. So then your values will only be forced in between 0 and 1, and you can see a lot of things happening here. Periodic orbits, chaotic dynamics, a lot of things. Okay. Here we will see whether it is possible to have chaos or not. Okay. How many of you think that it cannot exhibit chaos? Because it's just a linear function, no? Just a linear function, no non-linear. We are doing non-linear dynamics. But this is just a linear function. But I'll show you. Yeah, we'll see. We'll see whether it is the case. Okay, now you know how this map looks like, right? What was the map? xp plus 1 is 2xp mod 1. Okay. Now we want to compute the Lyapunov exponent of this map. Lyapunov exponent. Can we apply the formula again? So remember, h of x was the Lyapunov exponent. That is equals to limit p tends to infinity 1 over p sigma of log of the derivative of the function. How you will see? I will tell you that this complicated formula, how you can just intuitively understand. Okay. So if you want to understand something is increasing or decreasing, you can take the log. Okay, that's the one effect. And you are checking the derivative of the function. If something is increasing, the derivative has to be positive, right? Derivative has to be positive if it is increasing. So therefore, derivative plays a role here. And you are doing that for each of the orbit x. And then you are dividing it by p. Okay, fine. So you're just like taking an average quantity. Okay, that's the intuitive definition of the Lyapunov exponent. Okay. So can we find this here? Can you find what is dou f by dou x for the map? Just 2, right? Because 2x, just 2x. So dou f by dou x is equal to 2. So h of x is nothing but limit p tends to infinity 1 over p summation of ln 2, ln mod 2. What should it be? Any ideas? How many times you are iterating it? How many times you are iterating it? 1. Yes, p times. So h of x is limit p tends to infinity 1 over p into, since ln 2 is a constant and you are summing it for p times, it is nothing but p ln 2. Okay. What does this give us to? Limit p tends to infinity ln 2. It's just a constant, nothing else. It's just ln 2. So you can see that the Lyapunov exponent turned out to be ln 2. Can you find what is the value of ln 2 and let me know? What is ln 2 value? Good. What is ln 2? Soon. Greater than 0. Greater than 0, isn't it? Greater than 0, right? The Lyapunov exponent turned out to be greater than 0. What does this mean? It displays chaos. So it is chaotic. Yes, log and mod of derivative. Yes. You will never get always greater than 0. It depends on the derivative, inside derivative. Ln positive quantity ln x is ln any, if x is greater than 0, does that imply ln x is always greater than 0? All right. Plot ln x. You plot ln x. See how ln x looks like. Can you see how ln x looks like? What is ln 1? Check how ln x looks like graph. How ln x looks like in the graph. The graph and tell me. Tell me when ln x is negative. When ln x is negative, what range of x? So you saw that just a simple looking map like xp plus 1 is 2xp mod 1. Just a linear map. Only due to the mod 1, it induces a discontinuity. Do you understand that mod 1, if you add, it induces a discontinuity? Like slowly it will increase the value 0.1, 0.2, 0.4, 0.8. After it went to 0.81, the moment it crosses 1.6, it will be forced to bring down to 0.6. So suddenly discontinuity is there. So even though the function is linear, only because of the discontinuity, you are observing the chaotic behavior. And this tiny observation of discontinuous maps led the scientist create a totally new field known as border collision bifurcation. It's a totally new field. We'll not study this, but I wanted to tell you that it's really a wide field. Like even my supervisor is he's spending almost his uh, years already in this field. So he has been still working on, and more results are coming up, and it's a evergreen field. So No, not a periodic map. At what point it is discontinuous? You can see if you just reach at 1, maybe I can tell you exactly where it is discontinuous. Yes, the moment when it reaches 1, when the function reaches 1, it will be discontinuous, right? Because when it reaches 1 mod 1, it will force down to 0. Otherwise, it is just crossing that path, like it is going on, increasing. But the moment it touches 1 mod 1, it forces back to 0. So when the map touches 1, can you tell me? When the map touches 1, when the function value is 1, at xp equals to 1 by 2, at xp equals to 1 by 2, 2xp is 1. So at xp equals to 1 by 2, the map is discontinuous. And the derivative also doesn't exist here. Derivative of the map doesn't exist at x equals to 1 by 2 because at x 1 and it forces back to 0. So it is discontinuous also there. But I wanted you to show that this is one example of a 1D map where you can analytically, on the board, you can by hand compute Lyapunov exponent. This is only the map. This is only the map where you can do it. Other maps, Hanon map, logistic map, no, cannot. Sorry. Computer has to be used. So we are lucky that there is one map where I can show you the real example of Lyapunov exponent in action. Now let us consider another example. Okay. I'll show you another example where this discontinuity is there. You can see we'll derive a very nice result here. Very nice result. So xp plus 1 is 2xp. xp is less than 1 by 2 and it is 2 into 1 minus xp when xp is greater than 1 by 2. Again here x is belonging to 0 and 1. Yeah. So what it tells, when your x is less than equal to 1 by 2, you double it. Okay, you double the quantity. When x is greater than 1 by 2, you do twice into 1 minus that quantity. So you can see where the map is not continuous. Can you tell when the map is not continuous? Yes. Okay. Okay. So you can see, again, you can see what is f prime of x, like dou f by dou x, dou f by dou x. And we are taking the absolute value, mind you. Again 2, right? Dou f by dou x, absolute value is again 2. Isn't it? Absolute value, mind you. Absolute value. Yes. So dou f by dou x is again 2. If you do h of x, what you will get again? Can you tell? Limit p tends to infinity. 1 over p summation ln 2, right? Again, I. So again, it will be limit p tends to infinity. 1 over p times p ln 2 again. This is ln 2 again. Got the idea? So for this map also, for this discontinuous map also, you are getting the same Lyapunov exponent previous map. Okay. So it's a coincidence that the two maps have same Lyapunov exponent, giving a sense that the trajectory diverging is also of a similar fashion. Okay. So this also is greater than 0. So this map also show chaotic behavior. Chaotic behavior. Okay. So observe that, so this is one more important point. Observe that Lyapunov exponent here, Lyapunov exponent on space x. Therefore, it is h of x. Okay. And this is only happening when it is 1D map. We consider 1D map now. Now I'm asking higher dimensions. We move to higher dimensions. If we move to higher dimensions, we can discuss that in addition to the location x, it also depends on the direction also. It will take 2 into quantity, 2 into action. X, the point where you are computing Lyapunov exponent, and also the direction in which you are computing the Lyapunov exponent. Okay. So in higher dimensions, in one dimension only, the Lyapunov exponent depends on the point x. Therefore, h of x is written. You saw h of x, right? I never considered directions here. Never consider direction. But when you go to higher dimensional map, that is 2D Hanon map, 3D map, there you will take the point of the orbit and also the direction in which you are computing Lyapunov. We'll not go into detail, but yeah. Yes. So after the Lyapunov exponent, I just wanted to tell you something more, okay, about the coexistence. Hmm? Shall we discuss it today's class or next? Okay.